Hello. In this video, we are going to implement the finite element method for 1D scalar field problems in MATLAB or Octave. So we are going to use an example and first solve this example by hand in order to understand how the finite element method works in practice, and then we implement the same in MATLAB. Afterwards, we try to generalize the program so that we can solve the problem for any number of elements. We also post-process the result, that is, we use graph functionality to visualize the result and compare it with the exact solution. Okay, so let us assume this example. We have a 1D linear PDE, okay, in the domain spanning from -1 to +1, okay, in the x direction, and we have mu, which is like a diffusion coefficient. Okay, we take it as 1, and the source term f we also take it as 1. That is okay, and we have the following boundary conditions. On the left edge, we have a value of +1 specified. Okay, this is a non-homogeneous Dirichlet boundary condition, and on the right side, that is at x equal to +1, we have a value of 2 specified. This problem has a simple unretrieval solution which we can use to compare our result we obtain using the finite element method. Okay, so this is the unretrieval solution. Now, in the first process in the finite element method is that we first discretize the domain into a finite number of elements. Let us assume that we discretize this 1D domain into 4 uniform elements. So that becomes that HE, that is the length of the element, is the right side value of the domain, that is HR, the left side, that is XL divided by NE. So we have a constant element length. And for the time being, let us assume the element stiffness matrix and the force vector. In the next lectures, I am going to show you how to derive these quantities starting from the weak form or weighted, starting from the weighted residual statement, and then deriving the weak form, and then applying, and then like making the assumptions or approximations about the variation of the solution within each element. Okay, and then how to derive the element stiffness matrix and force vector. For the time being, for the sake of implementation, let us assume that we know the element stiffness matrix and we know the element force vector. So here we are assuming constant mu, constant material property, that is the material property is the same for all the elements, and since we have uniform elements, the length of the element is also the same for all the elements. Okay, so here we are going to use a two-noded element, that is each element is connected to 2 nodes. Okay, for example, the first element is connected to 2 nodes. That's why we have an element stiffness matrix of size 2 by 2. Okay, so this is a symmetric matrix, and here mu is the coefficient which is constant. Length of the element we will calculate. Okay, and similarly the force vector Fe is FHE, that is length of the element divided by 2, and then we have 2 by 1 vector. That is the force F is equally distributed between the 2 nodes. And remember that this expression for the force vector is valid only when F is constant. If F varies with respect to the x coordinate, then we need to calculate the element force vector in a different way. Okay, so now that we know the element stiffness matrix and the force vector, let's see how to solve this problem using the finite element method. Okay, so we said that we divide the domain into 4 uniformly spaced elements. So we get 5 nodes. Okay, so these points are called nodes. Okay, we have 4 elements. So element 1, element 2, element 3, and element 4, and we have 5 nodes. Node 1, node 2, node 3, node 4, and node 5. And these are the x coordinates of each node. Okay, so for the sake of implementation, for the sake of assembly of the element stiffness matrices into the global stiffness matrix, we prepared an array. Okay, so for each element, we identify the nodes it is connected to. Okay, each element is connected to 2 nodes, which is the first node, which is the second node. So for this problem, which is easier to identify, element 1 is connected to node 1 and 2, element 2 is connected to node 2 and 3, element 3 is connected to node 3 and 4, and element 4 is connected to node 4 and 5. That is why, that's what this table or this array represents. Okay, so we use this array for performing element matrix and element vector assembly into the global matrix and global vector. So before we do that, let us calculate the element stiffness matrix and element force vector. Since the value of mu is the same throughout the domain, so we have mu equal to constant, and we assume that we divide the domain into 4 elements. So we have the element length as 0.5. Using these two values, we can calculate the element stiffness matrix. So mu is 1, h is 0.5, so we get 2. So that means the element stiffness matrix is 2 minus 2 minus 2, 2. And similarly, we can calculate the element force vector. F is equal to 1, h is 0.5 and divided by 2. So we get 0.25. So when we multiply with the vector of 1 and 1, so we get 0.25 and 0.25. Okay. So this element stiffness matrix and element force vector, they are the same for all the elements. In general, they may be different if you have a mesh with a different lengths, and if you have a problem composed of multiple materials with different material properties. But that's a complicated problem. So for this simple problem, for all the elements, the stiffness matrix and force vectors are the same, and they are given by these expressions. Okay. Next, we need to calculate the stiffness matrix for the whole problem. Now that, okay, so we have 5 nodes, and at each node we have one solution. We have one variable, that is the field, the solution field. For example, it can be temperature. If you are solving a heat transfer problem, the solution field is temperature. If you are solving a diffusion problem, the solution field is the concentration. Okay, so since we have 5 nodes, and at each node we have 1 degree of freedom, so we have a total of 5 degrees of freedom in this problem. So that means our global stiffness matrix would be of size 5 by 5. Okay, so we have 5 rows and 5 columns. So we have entries from K11 to K55. And similarly, for the global force vector, we have 5 values, 5 rows, okay, from F1 to F5. Now, one of the important tasks in implementing the finite element method is to calculate this global stiffness matrix and the global force vector. This is our next step. So in order to prepare this global stiffness matrix K and global force vector F, we make use of this array. This array tells us to which rows and columns in the global stiffness matrix the entries of each element stiffness matrix would go into. Okay. In order to help you understand this visually, I have prepared an array. Okay, so we have a 5 by 5 matrix. So we have 5 rows and 5 columns. So this is our global stiffness matrix, and let us start with element 1. Okay, so for element 1, we have a 2 by 2 matrix, and it doesn't matter at the moment what these values are. Okay, First, let's look at these 4 black dots, okay, and see where they go into the global stiffness matrix. We know that element 1 is connected to nodes 1 and 2. So we have rows 1 and 2, columns 1 and 2. Okay. So that means these 4 values go into row 1, row 2, and column 1, column 2. Okay. So we know that element 1 is connected to nodes 1 and 2. So that means the degrees of freedom 1 and 2. So the entries of element 1 would go into row 1 and 2 and column 1 and 2 in the global stiffness matrix. That is, these values, we assemble these values into the global stiffness matrix into the first and second row and first and second row. Similarly, for element 2. Element 2 is connected to nodes 2 and 3, and the corresponding degrees of freedom are 2 and 3. Okay. So that means the values of the element stiffness matrix corresponding to element 2 would go into row 2 and 3 and column 2 and 3. So that is, so these 4 values would go into row 2, row 3, and column 2, column 3. So we have all the 4 values. Note here, in the diagonal entry 2 and 2, we have 2 dots. That means we have one value coming from element 1 and another value coming from element 2. So as you can see, node 2 is connected by 2 elements. There are 2 elements that are attached to node 2. So that means we get the contribution from both elements. That is what we see here. Similarly, for element 3, it is connected to 3 and 4. So it goes into row 3, row 4, and column 3, column 4. Okay. So these 4 values are populated into row 3, row 4, column 3, column 4. Similarly, at node 3, okay, node 3 is attached to element 2 and element 3. So we get entries from element 2 and element 3 into the diagonal entry 3, 3. Similarly, we assemble the element stiffness matrix for element 4. Okay, so this is how the symbolic assembly process works. Now, if you apply this to the numerical values, okay, then the procedure, we just apply this to the numerical value. The procedure is the same. In a similar fashion, we assemble the element force vector into the global force vector. For element 1, okay, so 2 values go into row 1, row 2, and for element 2, the 2 values go into row 2 and row 3, and so on. Okay. Now let us see how we do this using the numerical values. Okay, we know that this is our element stiffness matrix and this is our element force vector. We have seen the symbolic assembly. Okay, now let us see how the stiffness matrix looks like as we keep on assembling the element stiffness matrices. Okay, so we start with zeros and then we start adding the entries from the each element. So once we assemble the element stiffness matrix for element 1, this is how our global stiffness matrix looks like. So all the entries that are not populated are zeros because we start with zeros. Since we keep on adding the entries, we always start with zeros in the global stiffness matrix. So for element 1, it should go into row 1, row 2, column 1, column 2. So we have 2 minus 2 minus 2, 2 appearing in rows 1, 2, columns 1, 2. And then we add the element stiffness matrix for element 2. Okay, so this is the global stiffness matrix after we assemble the element stiffness matrix for element 2. Okay, here we have 4. Remember from the previous slide. So here in row 2, column 2, in the diagonal entry, we have 2 values. So we add them. Okay, so that is why we have 4 at 2, 2. Similarly, we assemble the element stiffness matrix for element 3 and then element stiffness matrix for element 4. Okay, as you can see in the diagonal, along the diagonal, except for the first and last entry, we have a value of 4. Okay, so that means we have added the contribution from both elements. Okay, in the same manner, we assemble the force vector, the element force vector into global force vector. For the first element, we have 0.25, 0.225. So they go into row 1 and 2. And then we add the element force vector from element 2. So since we already have 0.25 and when we add another 0.25, we get a total of 0.5 in row 2. And when we add the contribution from element 3, we have this as the global force vector. And similarly, when we add the element force vector from element 4, this is the final global force vector. Okay, so this is the final global stiffness matrix for the problem, and this is the final global force vector for the problem. Okay, if we put all of this together, we have the global matrix system as, okay, this is our stiffness matrix, this is our vector of degrees of freedom u1, u2, u3, u4 and u5 are the degrees of freedom at nodes 1, 2, 3, 4 and 5 respectively, and this is our global force vector, which is in a very like uh, format that is quite familiar to us, that is k equal to f. Okay, so we have assembled the element matrices into the global matrix and element vectors to global vector. Okay, we haven't used the boundary conditions. In the next step, we apply the boundary conditions. We know that u1 equal to 1. That is, at the left end, we have a specified Dirichlet boundary condition. So u1 equal to 1. And we apply the Dirichlet boundary condition in this manner. Okay, so this is one of the methods that we use to apply the Dirichlet boundary conditions. Okay, so in this method, what we do is we multiply the specified value of the degree of freedom, that is u1, with the corresponding column in the matrix. Okay, u1 correspond to the first column, so we multiply the first column with the value u1 and subtract it from the right hand side. Okay, and then we have another boundary condition on the right side, which is u5 equal to 2. And similarly, we multiply the corresponding column, that is column 5, with the value of the specified value, that is u5, which is 2, and then subtract it from the right hand side. So after using u1 equal to 1 and u5 equal to 2 and doing this calculation, we end up with the final global system with this force vector, which takes into account the boundary conditions. Remember, this is an important step. If you don't perform this step, okay, the global force vector would be different from the one that is supposed to be. Okay, we can ignore this step only when we have the zero boundary conditions, when the boundary conditions specified are all zeros. Okay, so don't skip this step, it is important. Okay, after we apply boundary conditions, we know that, okay, So we know that u1 equal to 1, u5 equal to 2. We can remove the corresponding rows, that is the first row and last row, first column and last column from the global stimulus matrix, and the first row and last row from the global force vector, and we can write the condensed matrix system and then solve it. Okay, so this is our reduced matrix system after removing the boundary conditions, after eliminating the boundary conditions u1 and u5. So we have a 3 by 3 matrix, 4 minus 2 0 minus 2 4 minus 2 0 minus 2 4, and then our unknown degrees of freedom are u2 u3 u4. On the right side we have 2.5 0.5 4.5. Okay, and then we can use MATLAB to solve this. So once we solve for u2 u3 u4, we get this as the solution. Okay, so we can plot this and compare it against the numerical, against the analytical solution. Okay, so this is how the finite element method works in practice. So when we are using some fewer elements, 1 or 2 elements, okay, in 1D, and like 1 or 2 elements even in 2D 3D, we can solve it by hand. But as we have as we refine the mesh, as we have like hundreds or thousands or millions or even billions of degrees of freedom, we can't solve it by hand, so we use computer. Okay, let's see how to implement this using MATLAB. Okay, so I'm going to use MATLAB live editor in order to visualize the result. Okay, so immediately, so okay, so we clear everything, we don't want to say anything. Okay, so we have the left hand as 0 minus 1, right hand as plus 1, our mu is 1, f is 1. Okay, let us say we so we said we start with 4 elements. Okay, so number of elements is 4, and then we have number of nodes as n element plus 1. Okay, okay, number of nodes, and then he we can calculate the element length, hr xr minus xl divided by n element. Okay, let's print it out. Okay, let's print them to visualize. Okay, now we need to prepare arrays. Okay, so from at this point we can calculate the element stiffness matrix. Let us denote this as ke. Ke equal to mu by he. This is multiplied by the tomato matrix with the values 1 minus 1 minus 1 1, and element force vector f he divided by 2, and this is multiplied by 1 1. Okay, so remember that this should be rows. Okay, that's why we use semicolon. Okay, so this is our element stiffness matrix, element force vector. Now, in order to assemble, we need the global stimulus matrix. Okay, so let's say kg K global. Okay, so our global should be of size 5, but instead of hard coding, let us create a variable total DOF, which is number of nodes multiplied by number of degrees of freedom. So for this problem, we have number of degrees of freedom as 1. Okay, number of degrees of freedom per node. Okay, it is 1. There is a reason why I do this like this, because with the future, if you are going to solve a problem with more than 1 degree of freedom, then it's we don't have to come back and redo all the calculations. Okay, no, our global stimulus matrix should be of size total DOF by total DOF. And similarly, we create a global force vector of size total DOF comma 1. Okay. Okay. Now we assemble element 1. To assemble element 1, we need to know what are the rows and columns. Okay. So here our rows and columns are the same. For element 1, it is 1 comma 2. Okay. So global rows. Okay. So our columns are the same as rows. Rows columns equal to. Okay. Remember, we need to add to the existing values. Okay. So K. Similarly, if global rows only. Okay. F global rows plus F here. Okay. If we run the code now, let's see what we see. Okay. So this is the global stiffness matrix after we assemble the element stiffness matrix for first element. Okay. So this matches with our calculations. Okay. 2 minus 2 minus 2, 2. And for the force vector, it is 0.25, 0.25. Okay. 0.25, 0.25. Similarly, we assemble for element 2. Okay. So here I'm going to copy this and then change the rows. Okay. 2, 3. 2 comma 3. Okay. Now, after assembling element in stiffness matrix and force vector for element 2, okay, this is our global stiffness matrix and this is our global force vector. We see here we have 4 in row 2, column 2, and we have 0.5 in row 2 in the global force vector. Okay, so we can always compare with our calculations here. Okay, similarly, we assemble for element 3. Okay, for element 3, we have nodes 3 and 4, so degrees of freedom 3 and 4. And for element 4, we have nodes 4 and 5. Okay. Okay. So this is the final global stiffness matrix after assembling all the element stiffness matrices, and this is the global force vector after assembling all the element force vectors. Okay. Next, we apply Dirichlet boundary conditions. We know that U1 equal to 1. So what we need to do, we need to subtract from the global stiffness matrix the column, so corresponding to the DOF. Okay, so we use the variable DOF. Okay, So corresponding to this, okay, so first column multiplied by u1, okay, and then u5 is 2.0. So for this DYF is 5, right? The end node it is 5, which is equal to end node. So the same, okay, create global DYF. Here we have u5. So we apply Dirichlet basis. Okay, so this is our global force vector after applying the Dirichlet boundary conditions. So notice that it changes once we apply the Dirichlet boundary conditions, especially when they are non-zeros. Okay, so we can again check with our calculations. Okay, so this is the value after we apply the boundary conditions. Okay, so it matches. If it doesn't match, then that means we have made a mistake somewhere in assigning these entries, okay, that degrees of freedom corresponding to the each element. Okay, now we solve for the unknown degrees of freedom. So in order to do that, okay, let us create an array, okay, DYF fits. Okay, so we have the first DYF fits that is specified, and then the last DYF, which is end node. And then we calculate an array DYF free. So we calculate it using set diff, like difference of sets. So we have an array of all degrees of freedom, and then we subtract from this DYF fixed. Okay, so with this we get all the degrees of freedom that are free, that is, that are unknown. Okay, now we need to solve this, but before we solve, let's go back here and then let's prepare an array for the solution. Okay, it should be of size total DYF comma 1. Okay, then we come to the boundary condition part. Okay, here now we know that the first DYF is u1, so we populate it to the solution array, and similarly we know that the last DYF is u5, we populate it to the solution array, and then at the end, that is after applying all the boundary conditions, we find the free DYF, okay, that is unknown solution, by subtracting. Okay, so first we can extract the matrix if you want to understand it. Okay, so DYF's free slash, okay, then F1, this is the reduced matrix and reduced force vector, okay, DYF's free comma 1, okay, and then the solution is K1 slash F1. Okay, so once we solve, we get the solution. Okay, let's say okay, so we have the solution. If you want, you can also create an array solution free DYFs, so which is K1 comma K1 slash F1, and then you can populate like this. Okay, so this is our solution that, okay, we have calculated by hand. So 1.625, 2 and 2.125. 1.625 to 2.125, and these values go into rows 2, 3 and 4. Okay, Now we can plot this. Okay. Let's plot this. To plot this, let's create an array node coordinates. So it goes from HL to XR. Okay, so like this. And then we calculate solution. Okay, so we can plot node coordinates from a solution. Okay, so we have plotted this. Okay, these stars are the solution at the nodes. Okay, you can connect them by line. Okay, now in order to compare with the unitary solution, we create another array. Okay, let's say we have this array. We create an array with more points so that we can have a smoother function, and then solution exact we have parameter solution is okay minus half x squared plus half x plus 2. Okay, so minus half x squared plus half x plus 2, and then we plot, let's say, comma solution exact, and then use this. Okay, so blue line is the unitary solution, which, like, since we have used more points, it is quite smooth, and the black line with the stars is the solution we obtained using the finite element method. So there are 4 elements, so we have 5 nodes. At the left end the value is 1, at the right end the value is 2, and in between we have values, some non-zero values. Okay, now we can also calculate the error. To calculate the error, so I am going to calculate solution exact 2. Okay, this we calculate at the node coordinates, because this is where we have the nodes. Okay, so error is solution minus solution z2, or we can do the other way. So the z solution minus the numerical solution. Okay, and we can plot the error. Okay, node coordinates and error. Okay, we create the second figure. Right, okay, so we have 4 values here. That's because, okay, so we have some matrix here which is not correct. So that's because one of the values, one of the arrays is a row or row vector, and the other one is a column one. So okay, so this is 5 by 5, 5 by 1, and this is 1 by 5. So what we do, we transpose one of them. Right, okay, so this is the error plot. Here, as you can, if you can notice carefully, here the value on the y-axis is of order of 10 power minus 16, which is already at the machine precision. And if you look at the values of the error, so we have order of 10 power minus 15 minus 16. So this finite element method for 1D problems, 1D linear problems, gives us nodally exact solution. That is why the error at the node C is 0 up to the mixing precision. That is, the solution we obtain using the finite element method using the 1D two-noded element for linear problems is exact. Okay, so this is how we implement finite element method in a computer. Like here we have used MATLAB. Okay, and as you may notice, we have hard coded this problem. That is, we are assembling the element stiffness matrices one by one. Okay, this is not really practical if you have thousands of elements. So how can we make generalize this? Okay, so I'm going to make modifications to the code to make it more general. Okay, so that it works for any number of elements. At the moment we have 4. Let's say we have 10 elements. Okay, before we make it for 10 elements, let's modify this. Okay, so that we can automate it for any number of elements. Okay, so one way to automate is not one option is here. We can use for loop over elements. Okay, so for element number 1 to NLM. Okay, so we want to automate this. Okay, so in order to make this for loop work for different elements, we need a way to access these different row values for each element. Okay, so for that, what we can do, we can create our table. Okay, we can create this table. So let's call that element node connectivity. Okay, so for this is for element 1. Okay, for element 2, element 3, element 4. Okay, we have only 4 elements. Okay, and then we create another array, element DOF connectivity. For this problem, both are the same, but for problems with more degrees of freedom per node, these will be different. So I'm using this so that you don't have to create more arrays later. Okay, so now with this array, what we can do, we can access the rows by accessing all the columns corresponding to the each element. Okay, so with this, we access the rows corresponding to each element, okay, from this array. Then our assembly process is the same. Okay, we're not changing anything. Now we can delete all of this code. Okay. Next, we can, okay, let's run the code and let's see if we get the same, if there are any errors. Okay. Right, okay, so there are no errors, we have the same result. Now let us increase the number of elements. See, as we give the number of elements, the size has increased to 11 by 11. Okay. Right, okay, we have an error. Index position something is wrong. That's because our element node connectivity is of size only 4 by 2. So we want to make this generic. Now, instead of again hard coding, we can use Okay, so if you want to test it before you implement, we can do this. Okay, so we have 1 2 2 3 3 4 4 5 and so on, and then we need to transpose it. Okay, so we have the element node connectivity array for any number of elements. Okay, and then the code will continue to execute. So it will assemble for all the 10 elements. It will apply the boundary conditions, and then it will find the solution at free DOF, and then it will assemble. It will add it to the solution array, and then we have the plot. Now, as you can see, the solution has done better. That is, with the mesh refinement, the solution improves. And the error plot, there is not much change in terms of the magnitude because the solution is nodally exact. Okay, so this is how we implement finite element code. We can also make more changes to make it more generic. Okay, so let us say, okay, we have implemented this and this is our code. Okay, we want to use functions. Okay, I'm going to copy this code. Okay, copy this code here. I save this. Okay, as FEM 1D exercise 1.8. Okay, so if you run this, it should work and give us 2 plots. Okay, so it gave us 3 plots because we haven't. Okay, so here we haven't created this. And then we close down. Okay, so we can make it even more generic. So for example, okay, instead of doing this here, so for example, if we want to implement for a different problem, and if your if your substance matrix and force vector are different, what we can do is we can create a function. Okay, calculate stiffness and force 1D to node 8, and then here we can pass node coordinates, so element node connectivity, so we need only the node numbers. Then we can pass whatever the information that we want to calculate. Okay, to calculate these values, and then we have this as a function. Okay, so here we can calculate HE. Okay, node coordinates. Okay, so we have first node. Okay, here we get our node numbers. So the first node is node nums 1, and the second node is node numbers 2. Okay, so that's our element length. So in this way, if we have elements of different lengths, we can automatically calculate the elements difference matrix. Okay, yeah, something is wrong because we don't have the node coordinates defined. So we move it to the beginning and we can delete this. Okay. Now we can make it even like we can run it for as many elements as we want. Okay. So that's how we implement finite element method in any computer code. Okay, so we can also remove this. So you can clean up the code. So you can remove unnecessary code from the one we started with, and you can also make this digital boundary condition. Okay, this into a loop. Okay, in order to make this into a loop, we can create one more array. Okay, solution. Okay, specified. We create an array here. Total div comma 1, and here we add the values. Okay, for the first div we have a value of 1. Okay, in the last div we have a value of 2. In this manner, we can add as many degrees of freedom that we have on the boundary for which we know the solution. Okay, and then we create a for loop. So we need to loop. Okay, we take 1 equal to I. Okay, so we loop it over the divs fixed array. Okay, so we have divs fixed array, and it is of size 1/2. So we need the value, the second value. Okay, we loop over this. Okay, so our div is div fixed. Okay, so we have the div. Okay, we delete this. Now here u1, let's call this value, carbonate twice, and this value is the values that we already populated in the solution specified array, then corresponding to the div. Okay, so for this to work, we need to move these two arrays to the beginning. Okay, so we move here. Now we have added loops for the element assembly as well as for the digital boundary conditions. Okay, the code should work. Now, again, as you can see, the advantage is, like for example, if you are solving a 2D problem or 3D problem with hundreds of devices fixed. So in this way, you can simply automate the application of boundary conditions. Okay, and then you populate the values specified here. Okay, okay. You can also avoid storing these temporary variables by directly using this. Okay, instead of storing temporary variable like K1 and F1, we can do this. And instead of storing the solution free DOFs, we can directly do this. Okay, right. Okay, so that's how we implement the finite element method here. Okay, so as you can see, the advantage of doing this is, for example, if you have a different problem, let's say advection diffusion equation in 1D, and we simply create another function for advection diffusion equation. We calculate the element stimulus matrix and force vector inside the function, extract them here, and the element assembly remains the same. Boundary conditions application remain the same. The solution is the same. Okay, we modify the exact solution if there is one appropriately, and then we create the plots. And if you have 2D problem, then this element assembly doesn't change. You need to change only this array, and we need to add a new function for 2D element to calculate the element stiffness matrix and force vector. And these two, they don't change, and the boundary condition application of boundary conditions, they don't change. Okay, so in this way we keep on making it more and more generic. So as we in the next videos, I will show you how to calculate the element stiffness matrices for more generic problems using quadrature points or gross points. I hope you enjoyed this. Okay, thank you.